Okay, so using the normal distribution to approximate the binomial distribution. This used to be far more significant before people had personal calculators that could work out factorials for them very easily and very quickly. However, it's still on the syllabus and it's still used and it still does make things easier. But what we need to do first of all is just recap that you can all remember about the binomial distribution. So, the binomial distribution. If something follows the binomial distribution, what do I write down?
Binomial number of trials and probability.
Yeah, n and p, that's right. N is the number of times you have a go at something, the number of trials, and p is the probability of success. Yeah. Okay, so that's true. And what is the mean of x? What is the mean of the binomial distribution? N times p. Yeah, that's right. The number of times you do it times by the probability of success. That gives you the average number of successes you will get. Okay, the values that x can take. What values can x take for the binomial distribution?
Between 0 and 1?
Between 0 and n.
Oh.
0 and n.
Between 0 and n, yeah. You can have no successes, 1 success, 2 successes. You can have no more than n successes. So what sort of distribution is x? I know it's binomial, but binomial is an example of a discrete distribution because it can only take a limited number of values as opposed to a continuous distribution. Yeah. Okay. Right, so with the binomial distribution, what is the probability x equals a specific value called r? What is the formula for working out binomial probabilities? NCR, which are you happy if I write it down like that? NCR? Not sure which way you did it in your 12.
Yes.
Yeah.
E to the x times q to the n minus x. Maybe.
Yeah, we've used R, but yeah, okay, you can do it that way if you like. What's Q then?
The probability of failure.
Yeah, that's right. Q is 1 minus P, probability of failure, okay? So that's a quick recap on the binomial distribution. Now, if we were going to do this question, so we'll have this as our first example, example number 1. If we have a fair dice, or fair die, it's only one of them, which is going to be thrown 40 times, and we are asked to find the probability of 10 or more sixes, if we're going to write this down as a binomial thing, what will x be recording? Number of sixes, yeah. So every time you do a question, write down what your letter is and what it's standing for. How is x going to be distributed?
X is binomially distributed with 40 attempts and probability 1 in 6.
Yeah. Probability of getting a 6 on a fair die is 1/6. That's the probability of success. N is 40. Okay. So that, if I want to write down in notation this line here, how do I write that line down in notation? I want the probability that x greater than or equal to 10. Correct. Okay. So assuming that you are born in 1950 and you have not got a scientific calculator that will just do this for you at the press of a few buttons, and you have to plough through all this handwritten calculations, what will you start doing now? What will you do? Crying? Quite probably, yes. But what would you have to do through those tears?
And work out
or whatever it is.
Okay.
Work out the probability of it for 0 successes, 1 success, 2 success, and then take up to 9 and then to
One step ahead of me, yes, you're right. I'll come to that one in a minute, okay? If you are not as intelligent as our last answerer, you would do the probability it's 10, the probability it's 11, the probability it's 12. That is definitely when you would start crying. And then you would go up to do the probability that it's 40, and you would add them all up. And each time you were doing that, you would be doing this calculation here. If you're a little bit smarter, you would say, actually, what I would do, that one there is actually the same as, well, it's the opposite of x being less than 10. So if I do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I've only got to do 11 of these things and not 31 of these things or 30 of these things as I'm doing here, which would save time. But do you agree it would take ages? Okay, so what we do is we approximate our answer. Now what I want you to do before I go any further is to find a page in your book, page 36, okay? I'll stick it on the visualizer as well, and it'll be seen on the video. There's page 36 in your textbooks.
Didn't they have binomial tables?
Yes, they would have had binomial tables. Even then, you'd still be doing quite a bit of work sometimes.
Right.
What we've got here is binomial distributions shown graphically. Along the top row, n gets bigger each time, but p remains the same, 0.1. On the bottom row, n gets bigger each time. It's the same value as for n as the graph above it. But p this time is a half. A half is, 50-50, sort of evens. And if you look at the shape of these graphs here, if you join the top of each bar, you would get, a bell curve. It looks like a normal distribution. And as n gets bigger, it looks more and more closely like a normal distribution. Now, p being 0.1, that's sort of like out at one of the extremes, like 0.1 and 0.9 would be sort of two extremes. And you can see here, that does not look much like a normal distribution, nor does that one. However, when n gets big, even with an extreme p-value, it looks relatively normal. So, when you have the right n and p combination for a binomial, you end up getting something that looks like a normal. So we just say, I don't want to do all that work, just going to use a normal instead. But when I said when you have the right n and p combination, your exam board says that is what we've got here. If n times by p is greater than 5 and n times by q is greater than 5, only if both of those conditions are met, then our binomial np can be approximated by a normal with a mean np. Well, you'd expect that, we already said the mean was np, and the variance, we didn't say earlier, but the variance of the normal is npq. So that is what you have to learn, those conditions. And every time you use this technique in the exam, you have to state those conditions and that they have been met. So, the most important thing that we need to write down now are the conditions for using the approximation. So the conditions are, if x is binomial np and np is greater than 5 and nq is greater than 5, only if both of those are met, then x approximately follows the normal distribution np, npq. Okay, those are the conditions for using the normal approximation to the binomial. Okay, and those you need to learn. Okay? So, if we return, one thing I'll say, not all textbooks and not all things will agree on these figures here, but your exam board, that will do. Okay? You may look in something for something else, or a book at university or something else, a high level book, and it might want stricter conditions or something. And different exam board might even want different conditions, but for your exam board, that is what they say is good enough. So if we go back to the question we had earlier, which is summarised by this bit here, I'm just going to write that bit down again. We had x was binomial 40 1/6, and we wanted the probability that x was greater than or equal to 10, and we decided that that was going to be an awful lot of work and we weren't going to do it. Are these conditions here met? So what you want to ask yourself is, can we use the approximation? So what you need to do is you need to work out what NP is. So NP here will be 40 times by 1/6. What is 40 times by 1/6? What's a 6 of 40? Go on.
6.6.
Yeah, 6.63. 6 2/3, which crucially is greater than 5, which means we're happy. First condition has been met. Then we need to check the other condition, NQ. What's Q? 5/6. So this answer is going to be 5 times that answer. So it's going to be in the 30s. It's certainly greater than 5. This means we're really happy because both conditions are met. And that value is actually... What is this value? 33 2/3. Okay, yeah, there we go. Okay, so both the conditions are met, so we can use the approximation. Okay, so we can say that as NP greater than 5 and NQ greater than 5, x will follow the normal distribution. And what is the mean? What do we use here? What was in our red box rule? NP. Okay, NP we worked out was 6 2/3. That has come from doing my n times by my p. And then my next thing was my NPQ, which we haven't worked out yet, but I'm sure you're just about to do it, and you're going to tell me that NPQ is... Yes. Okay, 5 5/9, if you don't have it at the top of your fraction. Okay? So we can now use this normal distribution to answer the question. Now, something else important happens which we've got to consider. Can anybody think of any issue that may need to be addressed? Okay, let's just carry on then. Right, let's see what happens. We wanted the probability that x was greater than or equal to 10.
We don't know whether it needs to be greater than or equal to, like, because it's continuous and you've gone from discrete.
Right, you've just used two important words. Shout those very two important words very loudly.
Continuous and discrete.
We have gone from a discrete distribution to a continuous distribution. You can't just do that willy-nilly without doing something about it. So, what I always get people to do now is this. Our original question was x based on the binomial distribution, and put that b in there, became x is greater than or equal to 10. But we are going to change that now into our x based on the normal approximation. Has anybody any idea what it will be? We wanted 10 or more. What do you think that will be if we switch from discrete to continuous? Where does 10 start? 9.5. Okay. Where does 10 start? 10 goes from 9.5 to 10.5, doesn't it? It's, that's what you've got to assume, really. So, what we have done here is we have used what's called the continuity correction. And you do need to be careful here how you use it. It will always be this number here, 0.5 above it or 0.5 below it. Okay, it will either there be 9.5 or 10.5. And it depends very much whether there's an extra line on this bar here, because this was discrete. That extra bar there on the inequality meant something in the discrete land. Okay? If that bar hadn't been there, if that had been x is greater than 10, what would we have written down over here? 10.5, yeah, because 10 could not have been included. So you've got to be really careful when you use this continuity correction that you get it right. Okay? So, our question is now become, I'm just going to write that line down there again. We are working out the probability that x on the normal distribution is greater than 9.5. Thinking back to what we did earlier today, why don't we like the way that's written down at the moment? It's not a less than in here, so what do we do?
1 minus p xn is less than 9.5.
Okay, we turn it round. We make it a less than here by doing 1 minus it. This number here is a continuous number. It doesn't matter here whether we put the extra bar on. We're back in continuous land now. We are in the normal distribution. Okay, right, what's our next step? What do we do after the p line? Phi line. Okay, what will go in this bracket? X minus mu. What is mu? Which is the same as the 6 2/3 I wrote down. Yep. Over sigma. What is sigma?
Root of
Yeah, that was the variance, so the root of that. Because that was the variance. So what I have here is that was my x, that's my mu, that's my sigma. It's always phi of x minus mu over sigma. Okay, you now need to work out the value inside that bracket as a decimal number. .202 is what I'm expecting it to be. You then need to go to your tables and find what phi of 1.202 is.
0.8853.
Says Mr. Lomax, and he is correct. Hopefully you could all find that in the tables. And then you do your subtraction and you get a final answer of
0.1147.
yeah. Okay. So we'll look at more of these next time. Okay, but that is it at first. Your only example so far of using the continuity correction. Why did you have to use it? Because you went from a discrete distribution to a continuous distribution. Why did you bother doing it? Because it saved you lots of calculating. Okay.